1. Given f of x equals 667.38 over x into 1 minus exponential negative 10x over 68.1 minus 40. Use initial guesses as x equals 1.0 and 2.0. I think this should be 10 as x equals 10 and 20. Question 2. X plus 3 sine x equals 2. Use initial guesses. X equals 0.3 and x equals 0.6. Question 3. 2 cos x equals exponential x minus 1. Use initial guesses. X equals 0.7 and x equals 1.0. Right here we have this condition. Take acceptable tolerance as 10 raised to power negative 7. Welcome, I am Matthew, and this is numerical space. Right away, let's see how we can use the bisection, the regular Fulsi method, regular Fulsi method to solve those questions. The regular Fulsi method is also called the false position method. This is it. False position. What does it mean? Very important in this lecture series are the following questions. 1. What is the regular Fulsi method? 2. How do we apply the regular Fulsi method to solving such mathematical functions? 3. How can we develop a simple code using a comprehensive software, technical of course, to solving such methods and other methods? At the end of this lecture, we should have answered those questions. Thank you. Let's begin. The Fulsi method uses the following recurrence formula. You call it a recurrence formula or an iterative formula. This is it. XR equals X subscript U minus XU minus XL f of XU over f of XU minus f of XL. This is one way of writing the regular Fulsi formula. Remember, I call this Fulsi. You can call it Fulsi. What we're interested in here is the mathematics, not the grammar. With this, XU, XL, of course, you have XR, f of XU, and f of XL. What do these things mean? If you look at each of these problems we have here, you will see two guesses are given. In the first problem, we have 10 and 20. In the second problem, we have 0.3 and 0.6. In the third problem, we have 0.7 and 1.0. The lower of the two numbers is what you call XL, and the greater of the two numbers in each of the curves is what you call XU. In mathematics, we may say XU is the upper bound and XL is the lower bound. U upper, L lower. And then R here, root for R. That's what each of those means. And when you have f of XU, it means in each of these functions, the function value, when you place the value for XU in place of X, wherever you have X, you use XU. Like in this example, in place of X, if I want to have f of XU, this becomes f of XU equals X here, U is 20. So you say 67.38 over 20 into 1 minus exponential 10 times 20, because x to u here is 20, divided by 68.1. Let's use XL, for example. If I want to get f of XL, in this case, wherever you see x, you place 0.3, because XL here is 0.3. You say 0.3 plus 3 sine 0.3 equals 2. The same thing follows. But the question, the very important question, is how do we get these values, XU, XL, and what do they really mean in the mathematics involved? Very important. But before I answer that question, let us see another formulation of the regular Fulsi recurrence formula. I said this is one way of writing it, you remember? Another way of writing the regular Fulsi formula is, please take note of this. If you have a pen and paper, you can take it down. Remove the U here and put L. Remove the U here and put L. That is all. Remember, that is all you need to do. So XR equals XL minus XU minus XL into f of XL. Every other symbols remain. It's just this and this that you change. Now note, if this is XU, this becomes f of XU. But if this is XL, this becomes f of XL. It's very clear. But how do we get these notations? To explain how we do this, let us use the following graphical illustration for a function y equals f of x. It's very important we understand what we mean by the root of a function. The root of a function, say f of x, is the value of x for which the function is equal to 0. Again, the root of a function, say f of x, is the value of x for which the function is equal to 0. With this graph, let us see what the root of this function should be. This is the actual curve. Look at this curve for the function f of x. You see where this curve cuts the x-axis. At this point, this is the y-axis. You will see the value of y here is 0. So actually, within this interval, xl, xu, the root of this function is here. xe, we've denoted that as xe, where e stands for exact. That's to say the exact root is xe. Now, why are we using xr instead of xe in our formulation and in this lecture? This is because the regular Fulsi method is a numerical method. And numerical methods in mathematics, sciences, and engineering do not give you exact solution. They give you approximate solutions. But the solutions are very much close to the exact solution. With a very robust method, you can even get an exact solution. But we're using XR. Now, XL and XU in our formulation are two values of x such that they bound the exact solution. That means xe lies between XL and XU. In this particular formulation for the regular Fulsi, XL is less than XE and XE is less than XU. Or better still, to write it comprehensively, you can say XL is less than or equal to XE, and XE, you can see it here, is less than or equal to XU. Now what the regular Fulsi method does is, from this graphical illustration, let's use the line PS. Look at this line, PS. From here, if you join, and where the line cuts the x-axis, call it R, so that you have PQRS going down vertically to T. SR is this point where the line cuts the x-axis. You will notice something. XR is closer to XE than both XL and XU. In the iterative formula, after getting the value of XR using that recurrence formula we gave, this becomes the new value for, in this case, XL. Look at what happens. When this becomes the new value for XL, let's roll down. By the time you join a line from this point down here, you would see it's getting closer to the exact solution. At some point, if you continue, it gets so close to the exact solution, and you know it's time to stop when what you call your relative tolerance is less than or equal to the acceptable tolerance given for this particular operation. In this operation, to solve these equations, we are given an acceptable tolerance of 10 raised to the power minus 7. Remember, in mathematics, when you say 10 raised to the power minus 7, it is the same thing as writing the acceptable tolerance equals 1, 2, 3, 4, 5, 6, 7. Then you place 1 there. That's the same way of writing that number. So at this stage, let us see how to use this formula. That takes us to the second question. How do we apply the Regula Fulsi method to solving problems? Given x plus 3 sine x equals 2, with the initial guesses 0.3 and 0.6. It is very important. Earlier, I mentioned the acceptable tolerance and the relative tolerance. You are given acceptable tolerance. With the Regula Fulsi method, how do you calculate the relative tolerance? To calculate the relative tolerance, use the following formula. Remember, also we have two formulas for XR. Let's release them again so we understand better. XR equals XU minus XL f of XU divided by f of XU minus f of XL. If you're using this formula, you calculate the relative tolerance using this epsilon relative equals absolute value of XR minus XU divided by XR, all multiplied by 100. Of course, 100%. But if you're using the other formula, which is XR equals XL minus XU minus XL, can you try this? F of what? Good. F of XL, because of this. Divided by f of XU minus f of XL. With this particular formula, what do you think will be the formula to compute the relative error? Try, look here, compare, what do we change? Okay, epsilon relative, which is the relative tolerance, equals absolute value XR minus XL. Yeah, this is XU, this should be XL over XR times 100. That's how to calculate the relative tolerance. At a stage when you observe that the relative tolerance is less than or equal to the acceptable tolerance, you stop your iteration. That value for XR is the result you're looking for. There you stop and take that as the root of the function. Now let us apply this to solving this question. when we have this given, what you do is reformulate this in terms of f of x. How do you do this? Take this 2 over the equality sign and change it to minus 2. So you have it as f of x equals x plus 3 sine x minus 2. Having it this way becomes very easy to solve. Now, we will be using this particular formula. XR, that is the first one. XR equals XU minus XU XL f of XU over f of XU minus f of XL. Note this formula. It's very important. How do we then use it? First, if you are not given the initial guess, that is XL, XU, and of course in virtually every other occasion when you go into the real world to apply this formula, nobody gives you initial guesses. You as the mathematician, or you as the engineer, you as the scientist, should be able to know what values you may take for XL and XU. Very important, the values you choose are such that f of x for those two values will not have the same sign. For example, if f of x, when you take the first value, is negative, take another value so that f of x at that point will be positive. That tells you that in between that interval there exists a root. That is how to choose. So here we are using 0.3 and 0.6. These are not fixed values. Remember, these are not fixed values. You can use 0.1 and 1.0. You know that the root lies between those values. Choose any value that f of x for both values will be of different signs. Now right here, how do we calculate XR? Call that iteration 1. Iteration 1, that's the first iteration. XR will be equal to XU, that's the upper bound, the upper value. There is 0.6 minus, bracket open, XU, remember, 0.6 minus 0.3, bracket close, times f of 0.6, which is f of XU, over f of 0.6 minus f of 0.3. Now, f of 0.6, remember, you calculate that by substituting 0.6 into this function. That is, this becomes 0.6 minus 3 sine 0.6, no, excuse me, 0.6 plus 3 sine 0.6 minus 2. And our trig function here is measured in radian, not degree. This is in radian. So when you get that using your calculator, do the same thing for 0.3. Find f of 0.3. You should be able to get the values.
Good.
Right away, from my calculation, f of 0.6 is 0.2939 and f of 0.3 is negative 0.8134. So all you have to do is substitute those values into this equation and get the value for XR. If you do this, please, I believe you can do that. Use your punch. 0.6 minus 0.3, of course, you have 0.3 times this value divided by this minus this. then whatever you have, subtract from 0.6. From my calculation, if you do what I have done, you'll get XR to be 0.5204. Tilting these values into X of R, you have this. XR equals 0.6 minus 0.6 minus 0.3 gives you 0.3 times f of 0.6, of course, there you have it as 0.2939 divided by f of 0.6 again, you have 0.2939 minus, this becomes minus 0.81, that is this, look at it here, 34. Now you have it. Do this multiplication out closely. We do this multiplication out closely. And of course the subtraction. You'll have 0.5204. This is to 4 places decimal in our calculations. Now you have this. The next step is check the relative error. Remember, the relative error with this particular formula is absolute value of XR minus XU over XR times 100. Where XR, substitute the value 0.5204 minus XU 0.6 divided by XR 0.5204 times 100. If you do this closely, you will have 15.3023, because that's percent. This is what we have after the first iteration. You see, this is quite greater than acceptable tolerance of 0.00000001. So you go over to the second iteration. But this is what you do. With the second iteration, you find the value of f of x given xr. That is to say, find the value of f of xr. If you substitute that into the function, remember, x here will be, let's just take this for example, 0.505204 plus 3 sine 0.5204 minus 2. Do this, you will get 0.0120. What does this tell us for our next step? Right here, you then have 3 f of x. Remember, f of xl, f of xu, and f of xr. You compare the values you have earlier. Anyone that has the same sign as f of xr should automatically take the new value for x. What do we mean? In our first instance, you will see here that f of xu, which is f of 0.6, is 0.2939. Take note. While f of 0.3 is negative. Take note of this negative. Here there is no negative. This is positive. This is negative. Negative 0.8134. It's obvious that f of 0.6 and this have the same sign. Positive, positive. So what you do now is you set, say, XL, XU to become 0.5204. Notice what I have just done. Because f of 0.6 has the same sign as f of xr, you then replace the 0.6 with the new value for xr, which is 0.5204. Note, if it were f of 0.3 that has the same sign, you would have replaced that with this. So this stage takes us to the next iteration, which is what we should call the iteration 2, or the second iteration. L remains 0.3, and our new value for xu will be equal to the previous value for xr, which is 0.5204. Now at this stage it becomes imperative we understand something here. We did that first evaluation for the f of xr to illustrate something, but in general you don't need to do that. Again, in general, if you're using the first formula, that is the one we are using now, xr equals xu minus xl.
As well.
In fact, xl will always remain constant with its formula. That is, for all the iterations, xl will remain 0.3. Why xu keeps updating to the value of xr. Now, the previous value, xr, is 0.5204. So, in the next iteration here, which is the second iteration, xu takes on this new value. So you then calculate a new value for xr. If you go to iteration 3, the same thing happens. xu will now take the new value we calculate here, while xl remains fixed. You continue the same till you get your result. Now, let us compute. With this, you find out, say, f of xl from our previous calculation is minus 0.8134, and remember f of xu will now become the f of xr, which is 0.0120. So with these values, you calculate the new value for xr. xr equals this 0.5204 minus 0.5204 minus 0.3 times f of xu, which is 0.0120, over f of xu 0.0120 minus 0.8134. Do this with your calculator, and what do you have? Right here, with my own computation, what I have, if you follow me closely, the same way I'm doing mine, we should have the same result. And from my calculation, what I have as my result, you have 0.5172. So at this stage, you calculate the new relative tolerance. Remember, to be the new value of xr is 0.5172 minus xu, but in this iteration, xu is 0.5204 divided by 0.5172 times 100, do that, let's see what you heard, Mr. Country. You now have 0.6239. You can see this is quite lesser than the initial value we have for this, which was 15 points. So, but still, this is greater than the acceptable tolerance. So, you go over to your next iteration, which is iteration 3. Just so you understand how it works. In the next iteration, XL remains the same, 0.3, while XU now becomes 0.5172. It keeps updating to the value of XR. You calculate the new value for XR. But you can see this procedure takes quite some time. In order to make it easier, and being in the digital age, we should learn how to use the computer software to write a program that executes this procedure. And in this video, the next few minutes, we should be able to do that and see how we can use our code, which we've developed, to solve these problems and others we started with. For this purpose, we should be using MATLAB, but we can have the code for Java and other languages on our website. Given a problem, to use the regular Fulsi method, these are the steps involved. 1. Already you are given the function y, say, equals f of x. The next step you do is to choose two values, the initial values for xl and xu, so that f of xl and f of xu is less than 0. And you simply know this is less than 0 if they have different signs. One is negative and the other is positive. Once you have satisfied this condition with two values chosen, you come to the next step, step 3. You calculate the value of xr using this formula. When you're done with that, you come to step 4. You evaluate the relative tolerance using this formula. After evaluating the relative tolerance, you check for this condition. This condition is also called the stop criterion. If the relative tolerance is greater than the acceptable tolerance, you set xu to be equal to xr, which we obtained from step 3. Then you go to step 3 and start all over. 3, 4, 5. Keep checking for this condition. If it's always greater than this, you repeat. But once you get to a stage where it is less than, you stop. There you already have a value for xr. The value of xr is the required root. So you take it, and then that's your result. Steps 1 to step 6 are the same as the algorithm you use in solving the regular Fulsi method. When you say algorithm, you understand what it means. A step-by-step procedure in solving a problem. 1, 2, 3, 4, 5, 6 is the algorithm. With these steps listed, you can write a simple computer code to solve any function using regular Fulsi. On our website, you have the MATLAB code for this. And using this code, which we have developed with these steps, let's quickly get the results for these problems, which we started with in this lecture. With the steps we developed earlier, we were able to write a simple MATLAB program that solves the problem. And these are the results. We got the value for xr to be 0.5170 to 4 places decimal, of course. You can extend it. And we got those results in 6 iterations. Now to check the accuracy of your results, you need to find the function value there. The function value, that is f of xi, which means f of 0.5170 is 8.7 times 10 raised to the power minus 10, which is quite a minute number. If you convert that, you have 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8, 7. Very small, tending to 0. That tells you the result you have is correct. Because the root, remember I said, is the value for which f of x is equal to 0. But here you can see the value and f of x is very close to 0. Then to check our relative tolerance, if it's correct. The relative tolerance from the program is 4.5 times 10 raised to the power minus 8. And of course you can translate this to 0 points, that's 1, 2, 3, 4, 5, 6, 7, 8, 4, 5. You can see this is less than 0.000001. This is less than this. So that tells you it's correct. Based on this, please, I gave this as a simple assignment for you to try. Try to solve number 1 and number 3 using the same methods. It will be lovelier if you can write the MATLAB program for it. Of course, you can get the program code on our website. But for now, you can watch this video over and over again to make sure you understand what we have done. Once more, I'm Matthew of Numerical Space. Thank you.